This is a continuation on the discussion of microseismicity induced by multistage hydraulic fracturing. Here I have updated my schematics in order to include fractures swarms that are caused likely by the segmentation of fractures in mixed mode propagation. If we remember, this is the concept of fracture segmentation due to mixed mode 1 and 3, and it's kind of difficult to draw this in 3 dimensions, but hopefully you can get the idea from this image over here of what I'm drawing over here, where we have sometimes these offshots of fractures due to this type of segmentation. So in red, I have drawn these main fractures, which are mode 1 or combinations with mode 1 and mode 2 and 3. And also we have a set of natural fractures here in gray, where reactivated fractures are also drawn in green. And superimposed to that, we have the events of microseismicity. The events of microseismicity are all these orange circles, where we can see that not everywhere we have microseismicity, but mostly on fractures created or reactivated in shear. And also you may see that I have added to this plot a fault over here, where if that fault gets fluid from the hydraulic fracture treatment, very likely is going to reactivate, and is if it's optimally oriented, and it's going to generate a significant micro or sometimes not such micro seismicity, and that's why we want to avoid these fractures and ideally map them before doing a hydraulic fracturing treatment. All right, so in this case, I wanted to highlight the mechanisms of microseismicity and what causes microseismicity. It's widely recognized that most of the microseismicity that occurs in this type of hydraulic fracture treatments is related to the fracture mode. Mode number 1 usually does not generate microseismicity because most of the energy just goes into separating the surfaces of the rock and also creating new rock surface, but that doesn't generate that much seismicity. Most of the seismicity comes from shear fracturing and from shear displacements, either mode 2 or mode 1. And we can imagine that in these simplified schematics, where we have one section of the rock sliding against the other in shear, and that event is the one that's going to generate the most energy in the form of elastic waves. Each of these dots is a hypocenter, which can be triangulated in order to obtain its location. But physically, all of these events of microseismicity are events of shear failure or reactivation. That means that the Mohr circle goes into the shear yield line. Something also very interesting to notice and very important to take into account is that some of this microseismicity can be produced by some of the fluid that leak off into the rock, like for example, say right here or right over there, that the fluid from the main fracture leaks off into the formation that changes the pore pressure and moves the circle to the left, getting the state of stress closer to the shear yield. But in some other locations, it might happen that also just the presence of the fractures may alter the state of stress such that the new state of stress reaches the shear yield without much contribution of the change of pore pressure in the rock. Both can happen. All right, so I wanted to take advantage of this video also to recommend a paper which explains very nicely microseismicity, going from the tools needed in order to to capture microseismic emission and going through the applications as well. So I'm going to post a link to this freely available document, and here you will see all the details about how microseismicity monitoring works and what are the applications. And for example, what we're going to see next is the concept of the stimulated reservoir volume, which is shown in this schematic, where each fracture stage, this is a top view, stimulates a certain area around each stage. All right, let me move this out of the way and continue with the discussion over here. All right, so the stimulated reservoir volume is going to be the region of the reservoir which feels the effect of the stimulation such that this area is going to be the area which is most likely to contribute to fluid flow once a drawdown of pressure is applied on the wellbore and also in the fractures. Why? Because we expect some of these reactivated fractures to be more conductive to fluid flow. However, the problem is not that simple, and that's what we're going to see right now. Before I go to that, let me tell you also that I have not taken into account in this case the fault, because that very likely is not going to contribute to the stimulated reservoir volume. In fact, you don't want to stimulate the fault because very likely you're not going to get any fluid out of that region. Okay, so now that we know what the stimulated reservoir volume is that area of the reservoir which shows significant microseismic activity, we could try to understand what links production to stimulated reservoir volume. You may think, and it's perfectly logical, that the larger the stimulated reservoir volume, the larger the production is going to be. And this is a trend which is shown over here, and which is a logical one, that the bigger the stimulated reservoir volume, the bigger the cumulative production. And where, let me add one equation over here, the estimated ultimate recovery of a particular location is going to be a volume, which is the stimulated reservoir volume, times the porosity of the formation, times the saturation of the hydrocarbon. Let's put it here as 1 minus the saturation of water, and that divided by the volume factor if we are considering oil. But basically, the larger the stimulated reservoir volume with this simple equation, the larger you would expect to be the stimulated ultimate recovery or the cumulative production, where I'm probably missing the most important thing over here. This has to be multiplied times the recovery factor. Okay, but there are cases in which we don't see such a great correlation between cumulative production and the stimulated reservoir volume. And there are some reasons for that. Sometimes, for example, you could have a very large stimulated reservoir volume, but very low production. And that might be the case in which you see a gigantic cloud of microseismic emission, but no much production after all, even though if you have a considerable hydrocarbon saturation. And the reason for that could be that you have unpropped fractures. In coming back to this schematic, in hydraulic fracture propagation, many times conducting proppant everywhere, it's very difficult, especially in these fractures which are reactivated in shear. Also, in some of these fractures that grow out of segmentation of other fractures, because of the turning and the tortuosity involved in such process, it's very difficult to get all of the fractures with proppant. In fact, field evidence shows that out of several fractures of these fracture swarms are created in reservoirs, just a few of them are propped. So here I try to make that emphasis with a thicker line showing what are the ones that are going to be propped. So you may have a lot of microseismicity, a lot of reactivation, but sometimes you may not have your proppant in there. So in that case, you're going to have a larger simulated reservoir volume, but a low production. A solution for that could be to utilize what are called micropropants, or also utilize acids to create etching on the surfaces of the fractures so that the fractures remain open. I was saying that they remain open, but probably not, the word is not open, but they remain with some conductive channels. So here, another solution for this problem could be to use acid etching on the fractures. On the other hand, you could have cases in which the stimulated reservoir volume is very small, but you have a large production. So how do you explain that? And there are at least two phenomena that could be causing such behavior. One is that you may have in this formation layers of high permeability that probably you're not aware of with most of the logging tools, but in many formations it's visible that you might have layers of high permeability that might be facilitating the draining of the reservoir. And the other explanation is that you could have what is called aseismic slip, which means that you do have fracture reactivation or creation in shear, but that creation does not emit seismic activity or significant seismic activity. And this is mainly the topic that I wanted to talk about in this short lecture. There are two types of shear slip, and these are called seismic and aseismic slip. This is something which is thoroughly investigated also in the geophysics community, because this is also how you explain that sometimes you might have a reactivation of a fault, and that fault could cause an earthquake sometimes, and some other times it doesn't. All right, so in order to characterize such response, let's think about an experiment. And this is the direct shear experiment, in which you have two pieces of rock, one against the other. You apply a normal stress, and also you apply a tangential force on the side, such that in the rock surfaces you have a normal stress and a shear stress. As you apply this tangential force, the rock is gonna oppose the movement by a shear stress and by a frictional force. And that shear stress is going to be proportional to the friction coefficient. Here, we're going to go a little bit further into understanding this friction coefficient because we're going to lump many other processes. In these processes of shear fracture reactivation, it's also very important to consider the velocity of the shear slip. And this friction coefficient, or also called an apparent friction coefficient, because it's going to, as I was telling before, lump many processes, is going to depend not only on the properties of the rock, but also on the velocity at which we measure that shear slip. That's also going to depend on pressure, on temperature, and also the pore pressure generated inside the rock as we have a shear slip. If you remember some time ago, we talked about drain and undrain loading. In some of these cases, you could have, during a large shear slip, undrain loading and also significant increases of temperature at the surfaces of the rock. And we're trying to put all of that together into this one number, which is the apparent friction coefficient. All right, so let's do the following experiment. We're going to displace these two sides of the rock and this is going to be the measured shear slip gamma, and that's going to be done at different velocities. First, we're going to do it at the velocity v1, and then we're going to do that at the velocity v2 larger than v1. So we're going to increase the velocity at that particular time. And depending on the rock and the conditions that I have, basically I can group this response in two. First, when I increase the velocity, very often, almost always, I'm going to see an increase of the apparent friction coefficient, an immediate increase. So this friction coefficient mu is going to increase. But after the velocity and all the processes here stabilize and I go into a constant velocity v2, there are some materials that are going to show a response in which the apparent friction coefficient decreases with increases of velocity. So velocity 2 is larger than velocity 1, and at a velocity v2 stable, the apparent friction coefficient is lower than at velocity 1. And this can be characterized by two parameters. The change from v1 to the maximum is usually go by the parameter A, and the change from the maximum to the stable velocity at velocity v2 goes by B. So whenever B is larger than A, I am in the presence of a material which is called velocity weakening. And this is the kind of material which is going to induce a seismic slip. Why? Because the energy that I had, or let's put it in terms of stress, the stress I was holding before was higher than what I can hold at higher velocities. So if shearing increases and the velocity increases, the material is going to get weaker and weaker, and therefore is going to release more and more energy. This is what is going to end up in a rapid release of energy because the material is getting weaker as the velocity is increasing. And this is what is going to cause seismic slip, and also this is what causes big earthquakes. We could also compare this kind of phenomenon to an unstable process in which having a shear slip at a very small velocity may be just in an unstable equilibrium. It might be in equilibrium, it might be holding some stress, but as soon as the velocity increases, that goes into an unstable process. So this one is an unstable process. All right, let's see the other possibility. There are some cases in which when the velocity is increased, as I told you before, the apparent friction coefficient is going to increase, but when it stabilizes, the apparent friction coefficient may be larger than what it was before at velocity v1. And in that case, the coefficient A is going to be now larger than B. Remember that A and B are measured from the maximum apparent friction coefficient, and in this case A is going to be larger than B, and this is what is called a velocity strengthening mechanism, and this is going to lead to what we refer to as aseismic slip. Why? Because when the velocity increases, the material gets stronger. And because it gets stronger, it can hold a higher stress than before. So in this case, this is not going to lead to an abrupt release of energy, but rather is going to take more and more energy every time. In this case, we can compare the aseismic slip to a stable process where this ball is going to be in the trough of this model. All right, so these two processes are very important to take into account, as we were saying before, when not only when we analyze events of microseismicity, as done usually for hydraulic fracture monitoring, but also for monitoring processes of fault reactivation whenever the pressure in a reservoir is changed as a function of time.